So we have talked about how to use the Bayesian deep learning framework for recommended systems. So now let's move on to how to use this Bayesian deep learning framework in the context of in the context of relational learning, social network analysis, and topic models. The problem setting here is that if we're given some graph where we have both the relations between the nodes and the content of each node. And more concretely, if we have a social network, then we will have the friend relations between each users, and we'll have the images and tags posted by each user. If we're given a citation network, then we will have the cited by relations between the articles, and we will have the text of the articles as the content. And the task is to learn a per node representation that captures both the content and the graph. And what we're proposing is a relational probabilistic autoencoder, where the deep component handles the node content and the graphical component handles the internal relation like citation networks or knowledge graph. And these two components is working together as a unified model so that we can enhance the representation power with the relational information. Here we're facing two challenges. The first challenge is how to take into account the graph when we're learning the representation. Basically, how to make the representation of two nodes closer to each other if they're connected in the graph. And the second challenge, of course, is how to handle multiple graphs. So for the first challenge, again, we will start with a probabilistic autoencoder formulation. Let me remind you that this one is a standard autoencoder, and this one is the probabilistic autoencoder that we proposed 5 minutes ago. And but instead of starting from the middle layer representation, this time we will start from the adjacency matrix that defines a graph. And we want to generate some latent vectors for each node, basically, from the adjacency matrix. Ideally, we want something like this. We want the connective items to be closer to each other in the embedding space. However, if we generate the embedding or the latent vectors one by one from standard Gaussians, there's no guarantee that the connected nodes can be closer to each other. So how do we solve this problem? Our idea is that instead of sampling or generating the latent vectors one by one, we propose to generate the vectors of all items as a single matrix from a Gaussian distribution, or more specifically, a matrix-varied Gaussian distribution, parameterized by the adjacency matrix. Here, the matrix Gaussian distribution, basically, it's gonna guarantee high probability density if the nodes are connected to each other, it's also closer in the embedding space. Now that we have figured out how to generate the latent vectors for each item, we can finally generate the middle layer representation x2 from a product of two Gaussians. The one of the Gaussian is related to the content x1, basically what document is about, and the second Gaussian is related to S, which is essentially the graph. So that X has information on both the documents and the graph. And this is the overview of the model. And these lambdas, again, they're just some hyperparameters to control the variance. And this is the overview. Note that this probabilistic autoencoder, again, is the deep component, and our relational part here is a graphical component to model the relational information. For the second challenge, note that this is already a hierarchical Bayesian model. So naturally, we can extend it to handle multiple graphs, like citation networks and co-author networks at the same time. More particularly, if we have to model Q graphs or Q networks, we only need this x2 to be generated from a product of Q plus one Gaussian. The first Gaussian, of course, will be about the documents, and the last Q Gaussians will be from the Q graphs. And after we learn this representation, we can use this representation to do whatever task we want. We can use this representation, for example, and train a tag predictor to predict the tags for each article. And here we show some results of article tagging for different methods. The M here is the number of tags predicted, and CTRSR is actually a variant of CTR that incorporates relational information. And interestingly, the autoencoder SDAE, even without the relational information, it can already outperform CTRSR. And with the relational information, our method, which we call relational SDAE, is able to provide a more significant performance boost. And in order to gain deeper insight into the difference between the baselines and our methods, we have another case study. Actually, we have two case studies. One is about an example article, and the other one is about an example movie. So for the first case study, this is a example article from, it's actually a conference paper from www, and it's a paper on sentiment classification. And we can see that the baseline essentially just recommend either irrelevant or trivial tags for this article. And our method is able to focus on the theme and recommend more relevant tags. The precision is 10% versus 60%. And this is the second case study where we have an example movie, E.T. from Steven Spielberg. And this is the recommended tags for the baseline, and this is recommended tags for our method. We can see that our method actually recommends 3 more corrected tags. And the last one in particular is very difficult to discover because it's not connected to any movies. It's not belonging to any movies connected to this ET movie. So it's very difficult to discover, but our method is somehow is able to find this tag. So to briefly summarize, we propose this relational autoencoder where we have this deep component to handle the node content, and we have the graphical component to handle the internal relation. And these two components unified into a probabilistic relational model for relational deep learning. And this model is actually the first deep learning model in the relational domain. It can naturally handle multiple graphs, and applications in article tagging also shows that our model can significantly outperform the state of the art.